right, hello students. Last class we did a lot of things with derivative rules, but we didn't prove the product rule or the quotient rule. So I wanted to go through the proofs of those, and they're very similar. And after I do the product rule, I'll show you just an alternate proof of the quotient rule using product rule and chain rule, because that's sort of the order that we prove things in. So let's look at a function. Let's say that h of x is the product of f and g of x. So then what I know is that the derivative of h is the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x all over h. One thing I've been trying to get across is that when you're proving something, that if you know something is already true, you try to make your expression look like what you want it to. I had a professor who said that the most powerful tool was wishful thinking. And so I know that I want f prime g and f g prime. And so what I'm going to do is just add something that kind of looks like f prime g. But I can't just add something out of the blue. I have to also balance out what I just added, f of x plus h times g of x. So I'm allowed to do that because all I really did was just added a very silly version of the number 0. See how that's all 0 right there? So I didn't change the value of the expression at all. But what I have now is I have two different things where there's a positive and a negative term. So I'm going to highlight the first chunk. This right here is positive, and this piece is negative, and they share in common f of x plus h. Similarly, this piece is positive, and this piece is negative, and they share in common g of x. So I'm going to rearrange them. I'll do the pink terms first, and then I'll do the purple terms second, and I will factor out the pieces that they have in common. So if I'm looking at the pink terms, both of the pink terms had f of x plus h. Then the one on the left had a g of x plus h, and the one on the right had a negative and a g of x. So that represents the two pink terms that I put in boxes. And then the purple terms had a g of x in common. And I'm going to rearrange it so that the positive f of x plus h is first, and the negative f of x is second. Now, because it was all over h, I can actually split it up to two different pieces that are each over h. And then I can distribute the limit across addition, because the limit of each of those pieces separately will exist. Okay, now I can even do some more distributing of the limits here. The limit of f of x plus h surely exists, and the limit of this surely exists, because that would just be g prime of x. Same idea here. The limit of g of x, well, that doesn't even depend on h, so its limit exists, and the limit of the other fraction also exists. And so I'm not going to write out the word limit 4 times, but that's what you do, is you'd write out the word limit 4 times, but what we end up with is f of x plus 0 times g prime of x, because that's the definition of this stuff right here. That's g prime of x. And then plus g of x, because there's no h involved there, times, same sort of idea here, this is f prime of x. F prime of x. And that's the common product rule that we normally see, where sometimes people abbreviate it f prime g plus f g prime, just if you flip-flop the order of those two terms there. So that's the product rule. That's the proof of the product rule. All you did was add in a silly version of the number 0, and you're allowed to do that because adding 0 doesn't change the value of the expression. And then you distributed the limits across addition and distributed them across multiplication, which you're always allowed to do so long as you know that each of the individual limits exists. So then now here's the quotient rule. Let's say that we have a function q of x, that's equal to f of x divided by g of x. And let's look at what q prime of x looks like. Same basic idea. F of x plus h over g of x plus h minus f of x over g of x, all divided by h. Oops, I forgot to write my limit as h approaches 0. What I'm going to do here is get a common denominator. And I'm going to pull the divided by h in front as a 1 over h, because that makes things a little easier to just kind of write. So to get a common denominator, the fraction on the left needs a g of x. So I'm going to multiply by g of x over g of x. And the fraction on the right needs a g of x plus h. So I'm going to multiply g of x plus h over g of x plus h, and we'll see what we get. So now I have a denominator of g of x times g of x plus h, and on the numerator I have g of x times f of x plus h minus f of x times g of x plus h. Now this should feel very similar to where we were on the previous problem. The only issue is we don't have anything in common on the numerator really to deal with. So we're going to add a version of 0 again. It doesn't seem to me to matter too much what version of 0 you add. I'm going to add in, let's add in a positive here, f of x times g of x, and we'll also add in a negative f of x times g of x. I'm not looking at my notes, so I think this is the right way to do it, because then we have here a positive and a negative term that have a g of x in common, and then here we have a positive and a negative term that have f of x in common. So really similar to what we were talking about just a second ago. So we have, again, limit as h approaches 0, 1 over h times, if I look at the pink terms, they have g of x in common, and then positive f of x plus h, negative f of x. And if I look at the purple terms, they have f of x in common, and they have positive g of x and a negative g of x plus h. This is looking pretty good. And the denominator has g of x times g of x plus h. Okay, one thing I notice is that the h, 1 over h can distribute. This part right here is looking a lot like a derivative, but this part is backwards right here. And so if that's backwards, what I can do is make this middle plus into a minus, and then it'll switch. Because if I have a negative out in front, this makes a double negative g of x plus h and a single negative there. All right, so I'm going to rewrite this. So we have limit as h approaches 0 of g of x times f of x plus h minus f of x over h. And then minus f of x times g of x plus h minus g of x over h, and all of that still has the 1 over g of x times g of x plus h. And so then what we're able to do is I'm going to kind of write on top of this in orange. So we have g of x times f prime of x minus f of x times g prime of x times 1 over, and if we plug in h equals 0, you can see that the denominator is g of x times g of x, which we call g squared of x. So if I had just a little bit more space on my screen, I would write that all out, but this becomes that formula that you've seen before, where you have f prime g minus f g prime, all divided by g squared. So there we go, we proved it. At the risk of this video getting way too long, we're going to show you the alternate way of proving that statement. So if we have q of x equals f of x over g of x, and here I'm going to assume that I already know the product rule, or I already know the chain rule. I can write that as f of x times g of x raised to the negative 1. So then q prime of x is going to be f prime of x times g of x to the negative 1 plus f of x times negative 1 g of x to the negative 2 times g prime of x. And we can rewrite that as f prime of x over g of x minus f of x times g prime of x over g of x squared, and then multiply this term on the left by g of x over g of x, which is just a funny version of the number 1, to obtain what we wrote, f prime g minus fg prime over g squared. So as you prove statements, you can use those statements to prove further statements, or you can go back to the definition and prove it that way. So if you're ever confused about what you're allowed to assume on a given problem, just ask me and I will clarify that. Thanks for watching. Please comment or ask questions if anything is confusing.